So today we will finalize our class. Okay, this is the last lecture, and previously we have learned about some NLP models, which is large in scale. So they are mainly composed of the transformer. Okay, and they are using some unraveled self-supervised learning first, using large amount of data which is unlabeled, and then they fine-tune those network pre-trained on large-scale unlabeled data to the specific task. Okay, and doing that, they are achieving the state-of-the-art, surpassing the state-of-the-art algorithms trained on specific data. Okay, we call that as the zero-shot setting. And BERT is another such models, which is actually producing better results than the GPT-1. Okay, and they are doing the self-supervision using this type of two tasks. Okay. Anyways, they are pre-training on the large amount of data, which is not having any labels, but making this type of tasks, they can train the network. Okay. And then fine-tune their network on the specific tasks in NLP. I mean, and GPT-2, 3, they are having the similar concept, but having larger architecture. And this is some variant of the GPT-3. And we can see this type of things. When fine-tuning on the specific domain, depending on the number of examples, their performance is increasing. As the larger number of fine-tuned training data supplied, their specific tasks performance is increasing, but even without given any training data for the specific data, the largest scale of GPT-3, their models is still doing something. Okay, so when the architecture becomes larger, the zero-shot capability, we call this as zero-shot because no number of specific domain data is provided. This is called as one-shot because just one sample is provided and few number of samples are provided. So we call that as few-shot. So, I mean, if the architecture becomes larger, the few-shot capability is becoming, we can possess this kind of few-shot capability. And the GPT-3, it is trained on large amount of text data. Okay. Okay. GPT-4, even larger architectures, and we are using, fine-tuning this GPT-4 for the chat application. So that's the thing we are using for the chat GPT nowadays. And we also learned about this clip and the approach that aligns the language and image, their encoder, text encoder and image encoder. Okay, so using this type of contrastive learning, we somehow align the output of text and image encoder, and we can do zero-shot classification using this clip method. Okay. So are you guys remembering this, right? So this amount of large-scale data was used to aligning the image and text encoders. And this is very interesting result, breaking the paradigm of previous CNN, the training data separately to the testing data. But even without this type of training data for the specific benchmark, even clip by aligning the image and text encoder using a lot of pairs of the image and text data, they can be generalized to the any benchmark. Okay. Sometimes it is less competitive than that domain's model, but still not bad. Okay. And this is also similar result to the GPT-3. So this is number of training data per class given for the specific domain data. But even without given that that specific domain's data, the clip is generalizing to that domain, okay, for the image classification task. And also, we also notice that even the testing data is their distribution is shifted to the cartoon or some sketch data. The clip is working. Okay? Clip, their performance is rather stable, but original CNN-based approaches, they are suffering a lot. Okay, when the data, their distribution is changed from the original data, which is used to train the original model. Okay. And also we have learned this kind of approaches, grounding Dino, which combines the text signals to the object detector. Okay. When doing that, this is the standard object detection task, which can perform object detection only for the pre-trained classes. Okay, so for example, bench, person, those are semantic classes where the training, the benchmark they are already having. Okay? But here, for example, World Cup and Year of the Lion, this type of object classes are not predefined in the training data, but even for those, unseen classes, by aligning the visual signals to the text signal, we can do this type of zero-shot object detection. Okay, and moreover, we can do this type of things as well. So among lion, we can select only the one lion which is located in the left. And also among many persons, we can find the one with his head up. Okay. So using this kind of text description, we can specify some object. Among other objects, we can discriminate, the object which follows these text descriptions. Okay. And grounding Dino, what they did is Dino, as I told before, that is the variant of DTR, okay, transformer-based object detector. Okay, so and this is somehow you can see this is the original DTR pipeline. So this is the input image and extracting some CNN, and this is some encoder of the transformer, and this is the decoder of the transformer. And originally, they are outputting the bounding box and class information, but they have another stream in the left. Okay. So here we have text input as well, and some backbones for the text. And in the feature enhancer, that is, if we magnify this part, it is like this. So somehow there are text feature and image feature, and we are combining this image and text feature via these two types of cross attention mechanism, and improve image and text features by somehow combining them. Okay, so that is happening in this feature enhancer part. Okay, so via these two types of cross attention mechanism, we are mixing some useful information in multimodal domains, the text domain and image domain, and improve those features. Okay, so this is the improved image and text feature. And then we further input it to decoder. Originally, we have to make some bounding box and class probability via this encoder, but here as well, we extract some patch-wise feature. And here we also estimate the text features, and similar to the clip, we are aligning this patch feature and text signals. Okay, so we are if we dot producting the dot producting this text feature and this patch feature, if they are similar, then their values are becoming close to 1. Otherwise, they are becoming to 0. Okay, so by aligning them using the contrastive laws, as in the clip, uh, at the inference, we can measure their similarity and can find the one that best matches each other. Okay, and by doing that, uh, we can somehow uh, achieving the goal here. Okay, so we can find some bounding box which is well matched to the text description. Okay. And also in the decoder, that is decoder layers are also magnified here. So somehow they are again combined with text signals, okay, in the middle. So here the original image features are somehow cross-attended with the text signal, and they are somehow here they are somehow also having the information combined with the text. Okay, so that's the design of this grounding dinner approach. Okay, are you guys understanding this concept? Okay. And also, this is not that important thing, but grounding dinner, they are also trying to model sub-sentence level text description. So this is visualizing the word level input. So each token of the transformer encoder, they are word in the sentence. But if you do the sentence level, then for each transformer encoder, the whole sentence is inputted, but sub-sentence level, either word or sentence are inputted for the encoder. So compared to the previous method, grounding denote, they are saying they are forced to have the sub-sentence representation, but previously there are either sentence or word. So they are somehow making their model more flexible than others. But this is also improving their accuracy, but not that significant technical contribution maybe. Anyways, this is the grounding deno. And there have been also approaches that want to extend the clip we have learned for the object detection task. Okay, so clip, as you learned, is the developed for image classification task. Okay, so giving whole images as the input, we want to reveal their classes for the whole image by assuming that they are only having just one main object. Okay, that's the clip. But region clip, they are wanting to extend the clip towards the revealing the region-wise features. Okay, so they want to describe the images contained in this bounding box rather than the whole image. So that's the thing the region clip is wanting to achieve. Okay, are you guys understanding this? Not very complicated, but I mean, this region clip is just wanting to extend clip to the region wise features. Okay? And originally, what they have done is clip, they are aligning the image text features, but for the whole images. Okay. So for the whole image, they are having this type of description, image description. Okay. And they are aligning by involving the language encoder, they are somehow extracting features for these sentences. And also for whole image, they are having visual encoder as well. So they are somehow applying contrastive learning on this whole image feature and language description. Okay. And by doing that, they can achieve the zero shot classification as well. But in the region clip, what they have further is these two more steps, okay, to aligning to aligning the patches with the region rather than the whole image. They are involving the vision encoder, another vision encoder that can describe the region, the cropped regions rather than the whole image. They are wanting to have another vision descriptor that can describe the patches rather than the whole image. And for each patch, they are extracting the region descriptions as well, right? So rather than the description for the whole image, they are wanting to describe these patches, okay? But using the same language this, encoder, they are aligning this patch-wise descriptor with the language encoders, okay? And by doing that, actually, I mean, for the extracted regions, they can anyways, I mean, some other extracted regions using the region proposal network, which was actually used for fast RCNN, this RPN, region proposal network. You may seen this in the fast RCNN. And in the inference, I mean, you can use this RPN network. And for the extracted patches, you can align the features with features extracted from language descriptors. Okay? So by doing that, actually, uh, this region clip, they are, I mean, getting the text descriptions for the regions. Okay, so I mean, this is the clip result, and this is the region clips result on the when for the regions, the patches. The reason why they separately developed this region clip is previous clip when applying clip for this, how to say, this specific region, then it is saying something wrong. So even though this object is umbrella, the I mean the the text which is most well matched to these regions are softball when we learn the clip, but when using this type of training method, then region clip, they are becoming to estimate this region as umbrella correctly. Okay. So the region clip, by explicitly having the vision encoder for the regions and having this region-wise descriptors, they are developing, extending the clips towards describing regions better. Okay. This is also similar. The clip fails to discriminate, to describe these sub-regions where they are failing to describe these regions, but the region clip, this paper is saying that they are better describing the sub-regions. Okay? But still, uh, region clip is failing sometimes. Okay? Glib is also similar method, which is developed for, I mean, grounding the each patches rather than the whole image. So if, I mean, I want to skip these details, but I mean, what they do is similar to clip, but similar to region clip. They are somehow aligning the patch-wise visual features like this patch-wise visual features to the patch-wise descriptions, text descriptions, okay? So what they do is when given text, they can match the word, specific word, okay, or in the sentence to the visual signals, okay? There has been approaches like this. Okay? And so nowadays, the object detection is also changing their paradigm. So previously, we have to train our model using the training data and test on that benchmark. But object detection as well, I mean, they can also do some unseen object detection. Okay? And also for the segmentation task, we are also changing our paradigm. And this is the foundation model for the segmentation developed by Meta. Okay. Originally, they were Facebook, but nowadays we are calling them as Meta. And what they do is they are also collecting large amount of more than 1 billion data for masks and images. Okay. And then they train the transformer-based large architecture uh, that can generate some masks from the images. But they are having some additional conditions. that help us to, generate this type of masks. The first signal is the point. Okay, given this point, when given this image and given additionally this point, they are generating some segmentation mask that have the, what to say, when let's for example, when person is here, okay, and when you give the point, initial point here, then the final masks are having the human masks. Okay. So, the point here is indicating the initial viewpoint for that region. So when we indicate point here, then the result have to have the whole masks. That include the point here, okay? And also we can give the initial conditions as the bounding box. And also we can also give some coarse segmentation mask, okay? Coarse segmentation mask as the condition to get the more dense segmentation mask as the result, okay? And also even we can use the text signals as the condition. So given this image and given this text, we have to get the mask segmentation result for that corresponds to this text signal. Okay? But these text conditions are sometimes weak. Okay, but SAM is working very good for these initial signals, their conditions. Okay. What they do is they develop some transformer-based method. They are having the image encoder. For this image input, they are having the image encoder. And for the prompt, they are encoding them as using the prompt encoder. And they are decoding by combining these two signals. They are making masks via the decoder. That's the same. Their architecture is very simple. So image encoder, and this is the prompt encoder, and this decoder is combining these two signals. So basically this figure is same as this figure, but having different style. Okay. So this figure is actually same as before. And in SAM, they are estimating 3 segmentation results. Okay. So empirically, they find that estimating 3 segmentation map is having better, possibility to, I mean, to, I mean, to satisfying the users. So they are estimating 3 segmentation masks. Okay. This is the same. Even though their architecture is simple, thanks to 1 billion training data, okay, this foundation model is working very good. And this is version 1. And nowadays, version 2 and version 3, as far as I remember, is appeared as well. So they are working very good. Okay, this is the example of the SAM. And one interesting result you have to remember is SAM, their result is quite close to the ground truth for multiple benchmark. This is the result for the multiple benchmark, and also higher is better. So ground truth, that's the best. But SAM, that is estimating 3 output, that is better than the SAM that is producing just 1 output. Okay. And this rhythm is the segmentation method that is using, transformer. Okay, so thanks to SAM, and also this rhythm is the method that is trained on the specific benchmark. Okay, but even SAM, they are not trained on specific benchmark. They are producing better result, better generalization capability compared to the rhythm. Okay, so, and here they are also measuring the, the performance for especially for the point conditions. So as I told you, here we can give some initial point to guide the segmentation mask. And this number is indicating the number of point for the point condition. And if you give more point, then their performance is generally, in general, becoming better. And SAM is best. And comparing to the state-of-the-art non-foundation model, SAM is getting better result. Okay? And when you are giving the point using some center object point, then it is the tendency is like this. And even for the case you give the point using the random point, the tendency is like this. Okay, and this is also similar result. You saw for the clip. So rhythm, that is the dedicated data set trained model. And SAM is compared in the zero shot manner. Comparing using 23 dataset, SAM is performing better even though it is not trained on specific dataset. But for some, because it is not trained on some data written in opposite way, they are trained on specific data. So sometimes it is weaker than this written, but most cases, SAM is better. Are you guys following this? And another thing is LangSAM. They are combining SAM we just learned with the grounding DINO. Grounding DINO we learned in previous lecture. So somehow SAM can input these bounding boxes as the initial condition, as I told you. So using grounding DINO, we can get fine bounding boxes that closely follows the text descriptions. Okay, so using grounding DINO, we can get bounding boxes which follows the text prompt we want, and then we can give that fine bounding box signals as the condition to SAM. Okay, and we call that as LangSAM because we can control SAM using, the text prompt. Original SAM is having the text prompt, but that is weak. So they are combining the grounding DINO with SAM and enhance the language understanding capability. And this is not paper, but some project open sourced in the web. So if you search for LangSAM, you can search for GitHub and you can use their code. Okay, so LangSAM, then using LangSAM, you can achieve this type of thing. So text prompt is person, then using grounding DINO, this type of bounding box is obtained, and using this as the initial condition, you can get these fine segmentation masks. Okay, and this is the GitHub of the LangSAM. You can test this following this link. So now, nowadays, the AI, even vision domain, their paradigm is now becoming shifted to the zero shot things, which does not require intensive training on specific benchmark. And another interesting approaches is text to image generation work. Okay, and we call this as T2I generation, text to image. So what they want to do is, given this text, they want to make some images. Okay, you already can do this using the even ChatGPT, okay, nowadays. But before ChatGPT, we developed some generative model that can do this type of things. And originally they were GAN or VAE, and gradually it is changed to develop some diffusion models. Okay, so I will explain about their few histories about this. So this is the example of the first T2I generator. I mean, previously GAN method. In previous lecture, we have learned about this GAN a bit, but GAN is also the method that is trained on specific data, but DALL-E is also developed by OpenAI. And they made first T2I generator, which operate in the zero-shot manner, okay, by combining a lot of text and image pairs. This DALL-E was first made, and that actually surpasses the capability of GAN. Okay, so for example, here, previous GAN is not properly making giraffe. Okay, even though the giraffe was the main object in this text, but DALL-E that can able to make the giraffe properly. Okay. So DALL-E was the first, I mean, zero-shot working T2I generator. And how they work is also using clip-like approaches. Okay, so they are first trained the VAE. So VAE, but this is some variant of the VAE using only image data. And then second method, they are aligning the text feature with their latent vector. Okay, so I will explain this part. So, I mean, this is the VAE. Okay, I mean, this is similar to having the encoder and decoder we learned before. Okay, VAE, but VAE they are somehow inputting the original input image, and their output is also the how to say the original image. Okay, they are trained to generate the original images. Okay, so in the first stage, what they do is using only image data, they are training this VAE. Okay, then by supplying a lot of billion scale images, this encoder and decoder, they are somehow learning how to capture the image characteristic and how to generate the images from these features. Okay, that's the first step. That's the first step. Using a lot of image data, they first train VAE part, and then they align text feature with VAE's latent vector, which means this is the latent vector of the VAE, and they are actually aligning this feature with another text encoder. Okay, so for example, here they are inputting some text, and they are aligning this text encoder with this latent feature. Okay, using similar to the clip. Then what they can achieve is given this given this text, they can generate latent vector, which is similar to the image feature. Okay. So, and then this using this decoder, you can generate images. Okay. Are you guys understanding this? Okay. So that is actually the first zero-shot working T2I generator. So given only text, from text, you can indeed generate images, okay? Because this decoder is seeing a lot of image data, so that is having very good capability to generate high quality images from this latent vector, okay? So their quality is good, was good. Even compared to previous GAN method, which is trained on specific data, this approach is producing good quality, better quality images. That was DALL-E 1. DALL-E 1. as far as I remember, this was, released this period. Okay. After that, diffusion concept have been, introduced. And what diffusion does is similar to encoder VAE. From the original image, this is the original image. To properly understand this diffusion, you have to take deep generative model, which will be held in AI graduate school. Okay, that is another course which is advanced. To properly understand diffusion model, you have to take that course. But in here, I want to briefly introduce the concept of diffusion here. And what they do is from the original image, rather than involving encoder and decoder, what they do is they are adding some Gaussian noise. They are adding some random Gaussian noise in the forward pass. And in the backward pass, this G is somehow the latent vector, similar to VAE. In diffusion, they are adding some Gaussian noise, like 1,000 times, okay, and then make this latent vector afterwards, and then doing inverse noise estimation. So somehow they are estimating the previous input by inputting it to the transformer. Given this X1 as the input to the transformer, they are estimating X0. That's the backward pass of the diffusion. So forward pass, we don't involve any network. Okay, we just add some noise. We can do that using OpenCV library. We can add some Gaussian noise to the original image. But for the backward pass, we are learning transformer to denoise this added noise. Okay, we train the transformer to denoise that. So that's like the decoder. Okay, for the encoder, we are extracting latent vector, but for that latent vector in the diffusion, they are slightly adding noise. But for the decoding pass, we are slightly denoise the images, and by applying transformer, that denoising transformer 1,000 times, we are getting back to the original image. That's the diffusion. And this concept is actually known to be robust, better, producing the higher quality images compared to the VAE or GAN. So later we are using diffusion model as our generative AI. In assignment 1 or 2, maybe 2, you are also having you have to train this type of network, right? Maybe. But nowadays we are actually using this diffusion model to generate the patches, okay? Anyway, but properly understand this, you may have to take graduate level courses. And this is also another challenging paper to understand, but I want to deliver some basic concepts for that. So this is the model that is called as latent diffusion model. So as I told you, the diffusion model originally add noise to the images themselves. Okay, so X0 was the image, and they are adding noise to get the latent feature. And by denoising them in the 2D image space, they are generating fine resolutional images. Normally, they do that in the image space, but LDM that is doing that in the latent space. So that's the difference. And this was the paper which is actually widely used in modern generative AIs. Okay, so you may heard about stable diffusion. This is one of the successful diffusion model that achieves the T2I generation, text-to-image generation, and that is actually based on this architecture. And their feature is very simple. Okay, what they do is this is the image encoder, and this is the image. They are first extracting the feature and apply diffusion process, which adds the noise 1,000 times on the feature space, not in the image space. That is why they are called as LDM, latent diffusion model. And then they are involving denoising network. This is the noised feature, right? And given this noised feature, they are involving some network to denoise them to the original feature. Okay, so the concept is same as diffusion model, but LDM they are doing that in the feature space. Okay, and then they apply another decoder to map this feature to the original image space. Okay, that's the LDM. And the reason why I told this, introduce this LDM is the DALI version 2, they are using this, additionally using this diffusion, okay? So DALI version 1, as I told you, they are first trained the VAE by supplying a lot of image-only data, and then align those image features to the text encoder, similar to the clip, right? And they achieve first T2I model, which is operating the zero-shot manner. And then in DALI version 2, that's the first step. Okay, that's the first step. What DALI version 1 does, that's the first step in DALI version 2. But in the second step of the DALI version 2, they are involving LDM to generate the images. From the latent vector, they are involving diffusion step to generate more high quality images. So, I mean, this image encoder is more having the DVAE architecture previously without denoising. But here in DALI version 2, their decoder is having diffusion process, denoising and noising steps they are having. So that's why DALI version 2 is producing better result than the DALI version 1. Okay. And this is showing the difference between the original DVA-based decoding step. AR is indicating that. And diffusion, this means having the diffusion process in the decoder. And they are producing better result compared to without diffusion operation, right? And this is also similar. On-clip is, they are saying their approach as the on-clip, having the opposite, I mean, operation to the clip, okay? They are doing the T2I rather than I to T, okay? So they are calling their algorithm as on-clip and using only the DVA architecture, and this is additionally having diffusion process, and they are saying by involving diffusion process, their quality is getting better. That's the DALI version 2, and their quality is becoming better. You can watch them. And another problem remained in the DALI version 2 was prompt following issue, which means when prompt becoming longer, the T2I image generator suffers to follow the text prompt well. Okay. So, so sometimes glasses are sitting on a table, but DALI 2 is generating some strange images not that closely following the text prompt. So that's the issue called as prompt following issue. So the remedy for this was, so here what they are describing is they want to involve more large scale language models that can understand complex text prompt. Okay, so they sometimes they at initial stage they are thinking that the reason why this DALL-E version 2 is not closely following the text prompt was their text encoder was weak. So in here, Imagen, their approach published here, what they did was they increased the capability of the language model, and indeed they found their performance is becoming better for following the text prompt. And another approach was proposing another large-scale data set that have complex prompt, including long, intricate textual descriptions and rare word and misspelled prompt. So that benchmark is called as draw bench, and they are enforcing the text descriptor by including larger scale language models and also by training them using this draw bench benchmark, okay, which have this kind of complex text prompt during training. And DALL-E version 3, as a result, they can now can produce proper images by following this more complex language prompt. Okay. And after that, nowadays, even ChatGPT is having the capability of this DALL-E version 3, right? Nowadays, vision language models, they are introduced and they are having better quality understanding of this longer text prompt, okay? And they can inherently have T2I generation capability nowadays. Okay, so the thing I want to deliver in this last lecture was, by involving large-scale learning and by aligning the vision models with the text signals, we can have better generalization capability, right? So the paradigm to have the training and testing split is nowadays changing, okay? And anyways, this is the promising way to achieve, generalization, okay? That was the conclusion, okay? And actually, this is the last lecture of this vision class. Okay, thank you. And so today we will finish here. And next Monday, as I mentioned, there will be a Q&A session and will be no attendance check. So if you have something to ask, please come. Okay. And next Wednesday, we have quiz 2. Okay? And the deadline for assignment 2 will be 24th of December. So okay, don't forget to submitting that. Okay? And we will also have the complaint period. After the final term, we are given a week to check your scores. So quiz 1, that is already in the Blackboard. Okay. And I also share the solution for that already, right? And quiz 2, we will also score them fast and share that in the Blackboard for the solution and score. And maybe after final term, we will have official, claiming period for 1 or 2 days. So if you think something is wrong in your score, then please mail me or TAs. Okay. Okay. That's the thing. Okay. So